Imagine this. An AI looks at a chest X-ray and actually performs better than human experts on certain kinds of tasks.
Yeah, it sounds a bit like science fiction, maybe from a few years down the line.
But some really groundbreaking research suggests we might be closer than we think.
Definitely.
So today we're taking a deep dive into this whole world of AI interpreting medical images. We're going to focus specifically on chest X-rays.
And on a brand new benchmark dataset that's really trying to push the boundaries of what these AI systems can do.
Our main source for this is a pretty significant research paper introducing this dataset. It's called ReXVQA.
That's the one, ReXVQA.
And our mission here really is to unpack this benchmark. We want to understand its approach, how it evaluates AI differently.
And crucially, look at its findings. Some of them are quite surprising, especially around this whole human versus AI comparison.
See what it all tells us about where medical AI is right now.
Oh,
Okay, let's dive in.
okay. So, first off, I think we really need to appreciate just how complex the job of a human radiologist is when they're looking at a chest X-ray.
Oh, absolutely. It's way more than just, ticking boxes or saying yes or no to a list of conditions.
Exactly. They're doing all sorts of cognitive tasks simultaneously, like pinpointing exactly where a finding is.
Localizing it.
Yeah, localizing. Or comparing the current scan to previous ones. Has something changed?
That comparative analysis, super important.
And maybe the most complex part, offering differential diagnoses. So, given everything they see, what are the most likely reasons for it?
That deep reasoning.
And that depth, that complex reasoning, is exactly where AI systems, even the really good ones, have kind of struggled traditionally.
Right. We've seen AI get great at classification tasks, like detecting pneumonia with, near radiologist accuracy sometimes.
For that specific task, yes.
But they're narrow. They couldn't really do that broader analytical thinking, that sort of expert assessment piece.
And a big part of the problem is the data used to train and test them. The data sets just weren't up to scratch for this kind of complex reasoning.
You mean the earlier medical VQA visual question answering data sets?
Yeah, things like VQA, RA, ImageQA, VQA Med, those kinds of things. Many of them use, simpler question formats.
Often template-based, wasn't it? Like, is finding present?
Pretty much. Often rigid templates, focusing mainly on just checking if something was there or not. They didn't really capture the flexibility, the sort of multi-step thinking that happens in a real clinical setting.
So there was this gap between the tests AI was taking and the actual job.
A significant gap, yeah, between the training data and the real cognitive work.
Okay, so then how does ReXVQA try to bridge that gap? What makes it different?
Well, the paper introduces ReXVQA as, and this is pretty bold, the largest and most comprehensive benchmark for chest radiology VQA to date.
The largest, right. What was it? Nearly 700,000 questions.
It's about, around 696,000 questions paired with 160,000 chest X-ray studies.
And crucially, not just from one place. The data comes from 4 different U.S. health systems.
Right, using different equipment from various manufacturers. That's key for reflecting the kind of real-world variability an AI would actually face. You don't want it just trained on one hospital's specific setup.
Makes sense. So what's the core innovation here in how it evaluates the AI?
The big idea is to evaluate AI not just on, one overall score, but on 5 distinct cognitive abilities, skills that directly mirror what radiologists do in their clinical workflow.
Okay, these are important. Let's list them. There's assessing the presence of a finding.
Is something there?
Analyzing the location of it.
Where is it, precisely?
Detecting negation. This one seems really key.
Super critical clinically. Is something absent when you might expect it or need to rule it out?
Right. Then proposing differential diagnoses.
What could this be?
And finally, geometric reasoning, like measurements or spatial stuff.
Exactly. How big is it? Where is it in relation to other things?
And the way the questions are distributed reflects clinical practice too, doesn't it?
It does. Negation and presence questions make up the vast majority, around 72%, which makes sense. That's a lot of what radiology reporting involves.
Okay. And then differential diagnosis.
That's about 21%. Location analysis is around 6%, and geometric is a small fraction, less than 0.5%. So the focus is definitely on those core reasoning tasks.
Okay, building something like this scale, this clinical relevance, sounds incredibly difficult. How did they make sure the questions were actually good, clinically authentic?
They talk about this quite a bit. They used a really rigorous expert-guided pipeline. 3 main stages: generation, quality check, and then validation.
And the source material is interesting too.
Yes. This is a key point they emphasize. They only used existing radiology reports to generate the questions.
Not the images directly.
Not for generating the questions themselves, no. They started exclusively with the text reports. And the reason is crucial. It helps prevent what they call multimodal hallucination.
Where the AI might kind of invent findings by trying to mash up image and text info incorrectly.
Exactly. By starting only with the radiologist's verified text description, the questions are grounded in actual confirmed clinical observations from the report.
Okay, clever. So they start with these expert reports. Then what happens?
Well, the reports get transformed into structured bullet points. They mention using an LLM for this specific step, GPT-4o, actually, but just as a tool in the pipeline.
Right, not one of the models being tested later.
Correct. Then those bullet points are turned into multiple choice questions, MCQs. And they apparently went through like 12 rounds of refining the prompts for this based on feedback from actual radiologists.
Tweaking it to make sure the questions were clinically sound, clear, well-formed.
All that.
And why MCQs? Multiple choice. Seems a bit restrictive, maybe.
Well, their justification makes sense for a benchmark. First, MCQs are very common in medical education and board exams, so it's a familiar assessment format. And critically, for a huge data set like this, MCQs allow for systematic objective scoring. It's much easier and more consistent to grade than free text answers, especially across many different AI models.
Okay, standardized evaluation. Makes sense.
Yeah.
But how do they actually check the quality of, nearly 700,000 questions?
That's where the quality check and validation stages were vital. They had automated checks, structural checks, content relevance, even compliance checks using tools like ClinicalBERT to flag any potential protected health information.
So automated filters first.
But then, the really critical part, expert review. They had board-certified radiologists manually review samples of the questions.
What were they looking for?
Clinical accuracy, clarity, making sure the question was correct, that the answer options made sense, and that the question actually aligned with the provided X-ray image.
Did they find problems initially?
Oh yeah. The paper is refreshingly transparent about this. Initial reviews found issues, things like questions having more than one plausible answer, or making unnecessary comparisons, or even clinical validity problems, maybe hallucinated findings creeping in despite the process. But the key is that finding those issues led directly to improvements in their generation pipeline. They refined it based on that feedback, and they report that later batches had minimal errors.
That iterative process driven by expert feedback sounds crucial for building trust in the benchmark.
Absolutely. That level of rigor is pretty impressive.
Okay, so now they have this high-quality, clinically relevant benchmark. Which AI models did they actually test on it?
They put 8 different models through their paces, all described as state-of-the-art multimodal large language models at the time.
A mix of models, I assume. Some specialized for medicine, others more general.
Exactly. The list included MedGemma 4B, that one's more medically focused, but also 𝐸N 2.5 VL, Janus Pro 7B, Eagle 29B, Gemini 1.5 Pro, Olivia 535, and 𝐸N 2 VL. A real spectrum.
And just to be clear, none of these were the GPT-4o they used inside the question generation pipeline.
Correct. Totally separate set of models being evaluated.
So the test itself, what did the models get and what did they have to do?
Pretty straightforward setup. For each question, the model received the X-ray image or images if multiple views were available.
Okay.
The natural language question itself, and the 4 multiple choice options, A, B, C, D.
And the output required?
2 things. Select the correct option, and importantly provide a detailed explanation for why it chose that option.
The reasoning matters too. And the main metric was just accuracy.
Standard accuracy, yeah. Did it pick the right letter?
Okay. Now for the really juicy part.
Yeah.
The results. How do these fancy AI models actually perform on ReXVQA?
Well, the overall performance, it varied a lot.
Big range.
Huge range. The top performer was MedGemma. It achieved an overall accuracy of 83.24%.
Wow, over 83%. That sounds pretty good for such complex tasks.
It is, but compare that to the lowest performer,
Who was that?
Olivia, which came in at just 26.61%.
26%. That's
Yeah.
barely above random chance for 4 options.
Exactly. So this massive gap really highlights how differently these models handle this kind of complex multimodal reasoning task. Even models considered state-of-the-art can have wildly different capabilities here.
Did they break it down by those 5 reasoning skills? Did models show specific strengths or weaknesses?
They did, yeah. Table 2 in the paper shows this breakdown. And MedGemma, the top overall performer, actually led in 4 out of the 5 skill categories.
Which ones?
It was best at differential diagnosis, around 77%, geometric reasoning, over 80%, location analysis, about 83%, and presence assessment, hitting over 85%.
Okay, dominant across the board mostly. What about negation, that clinically critical one?
That one was incredibly tight at the top. Actually, 𝐸GL2 just edged it out with 86.32% accuracy.
Really?
But only just. Gemini 1.5 Pro was right behind at 85.68%, and MedGemma was effectively tied at 85.03%. So the top models are all getting very good at spotting when something isn't there, which is great to see.
Interesting. So different models might have slight advantages in different cognitive skills. It's not just one monolithic intelligence.
Precisely. It suggests that maybe future medical AI might need specific designs or training tailored for different types of clinical reasoning.
Did they dive deeper into MedGemma's performance, like across different types of findings or parts of the body?
Yes, tables 3 and 6 give some fascinating detail there. It really shows where that specialized medical training seems to pay off.
Like where specifically?
Well, MedGemma showed incredibly high accuracy on questions related to heart findings, over 97%.
Wow.
Also really strong on spine findings, almost 93%, ribs, nearly 92%, and even things like tubes and lines, which can be tricky, over 83% there. Pulmonary neoplasms, too, almost 89%.
So the domain-specific training appears to give it a significant edge, even maybe boosting performance in areas where general models might otherwise seem okay.
That seems to be the clear message, yes. For these really complex, high-stakes medical tasks, that specialized knowledge baked into the model currently makes a big difference.
Okay, this all leads us to the finding that got a lot of attention. The direct comparison between AI and human experts.
The reader study, yeah, this is where it gets really interesting.
So tell us about how they set that up.
They took a random sample of 200 cases, image and question pairs from the ReXVQA benchmark.
Okay.
And they had 3 human radiology residents interpret these 200 cases. They had to answer the exact same multiple choice questions that the AI models answered.
So a direct head-to-head on the same test question.
Exactly.
Yeah, headline result, the big takeaway.
This is the milestone moment, the paper flags. On that specific set of 200 benchmark cases, MedGemma, the top AI model, achieved an accuracy of 83.84%.
Okay, consistent with its overall score. And the humans.
The best performing human radiology resident in their study scored 77.27% on those same 200 cases.
Wait, so the AI model, MedGemma, scored higher than the best human resident they tested.
That's what the data showed, a difference of over 6 percentage points.
On this specific benchmark evaluation, the AI outperformed the human experts involved in the study.
Yes, and the paper explicitly frames this as basically the first time they're aware of where an AI has consistently exceeded expert human evaluation in chest X-ray interpretation on this type of comprehensive, clinically focused benchmark.
That feels like a really significant step, potentially huge.
It's definitely a noteworthy result, but there's always a but, isn't there?
Usually is. Does getting a higher score mean the AI is actually reasoning like an expert radiologist?
Ah, that's the critical question. And the inter-rater agreement analysis, shown in Figure 5, adds a really important layer of nuance here.
What did that show?
It showed first that the human radiologists generally agreed with each other. Strong human-human agreement. They were largely seeing things the same way, coming to similar conclusions.
Okay, that makes sense. Consistency among experts.
But the agreement between the human readers and the AI models, including MedGemma, was noticeably lower. Interestingly, the human-AI agreement was pretty similar across the different AI models tested.
So humans agree with humans. AI models might agree more with other AIs than with humans.
Kind of, but the key point is the lower agreement between the human experts and even the best-performing AI.
So if we connect that back, what does that lower human AI agreement suggest about how the AI is arriving at its answers, even the correct ones?
It strongly suggests that while an AI like MedGemma can achieve really competitive, maybe even superior results on this benchmark test, it might be getting there using different methods.
Different diagnostic pathways, different reasoning processes.
Potentially, yes. It might be picking up on different visual cues or weighing factors differently than a human expert would. It gets the right answer on the multiple choice test, but maybe not by following the same clinical logic or thought process.
That definitely raises a profound question, doesn't it? If an AI gets the correct answer but uses a non-human pathway, does that still count as expert-level clinical reasoning, especially in medicine? where the why can be as important as the what.
It's a critical point for discussion, for future research, and definitely for thinking about clinical implementation. It's not just about the score.
Okay, so let's try and synthesize what this ReXVQA benchmark and these results really mean for the field.
Well, first, ReXVQA itself seems like a valuable contribution. It pushes evaluation beyond simple classification towards these more complex, clinically relevant reasoning skills. That's a step forward.
Definitely seems to measure things closer to actual radiology work.
Second, the results really hammer home the value of specialization, at least for now. MedGemma, the domain-specific model, just blew the generalist models out of the water on most tasks.
So for high-stakes medical AI, investing in that specific domain training seems absolutely essential right now.
It certainly looks that way based on this evidence. Generalist models might be impressive, but they're not yet consistently matching specialized ones on these tough medical benchmarks.
And then there's the AI beating human experts finding.
That milestone, yeah. An AI exceeding expert human performance on this specific benchmark is undeniable progress. It shows the potential for AI to handle complex reasoning in medicine is increasing rapidly. It's a step towards potentially more capable, maybe even generalist, medical AI systems down the road.
So thinking about the implications, what does AI getting this good at reading X-rays mean for, for our listeners, for healthcare in general?
Well, the potential upsides are clear. You could imagine faster initial reads, maybe more accurate diagnoses eventually. It could be huge for tackling radiologist shortages, especially in underserved areas.
Improving access to expert-level interpretation, maybe?
Potentially, yes, but it does raise that big question. How exactly might this kind of AI capability be integrated safely and effectively into actual clinical practice to improve access and quality? It's not straightforward.
No, definitely not. And we should also mention the limitations the researchers themselves pointed out.
Absolutely. They're candid about them. The data set, while diverse for its U.S. sources, might not perfectly represent global populations or practices.
Different disease prevalences, different imaging protocols elsewhere.
Exactly. Also, they only evaluated these 8 specific models. There might be other commercial or private models out there with different performance characteristics.
And the MCQ format itself, well, great for benchmarking.
Doesn't capture everything. It doesn't replicate the completely free-form, dynamic reasoning and discussion a radiologist might engage in for a really ambiguous or complex case. It's a proxy, a good one, but still a proxy.
Okay, so wrapping up then, key takeaways from this deep dive.
We looked closely at ReXVQA, a new benchmark designed to test AI on clinically relevant reasoning skills for chest X-rays, going beyond simple classification.
We saw it breaks down reasoning into specific cognitive tasks like location, negation, differential diagnosis.
And it's backed by this really rigorous expert-guided pipeline using real radiology reports to ensure the questions are high quality and clinically grounded.
The results were pretty striking, especially MedGemma, the specialized model, performing best overall.
And the headline finding, MedGemma actually exceeding the accuracy of the human radiology residents tested on that specific 200-case benchmark sample, a significant milestone.
But with that crucial nuance from the agreement analysis.
Right, suggesting that the AI, even when accurate, might be reasoning differently than the human experts. It's reaching the destination, perhaps via a different route.
Which leaves us with a final thought to chew on. Given these potentially different reasoning patterns and knowing the limitations of even advanced benchmarks like ReXVQA, what does it truly mean for an AI to achieve expert-level medical reasoning?
And what are the big, complex hurdles, technical, ethical, regulatory, that still remain before systems like these can be widely and safely adopted into everyday clinical practice? It's more than just hitting a score on a test.
Lots to think about there.
Definitely. And for anyone who wants to dig deeper, the researchers have made the public dataset and the AI model leaderboard available online. You can find it at rexrank.ai.
Good to know. Thanks for unpacking all of that.
My pleasure. Fascinating stuff.